In this video, you're going to learn what happens to your power output, fat oxidation, and lactate concentrations during a 6-hour simulated bike race. Hopefully, you can use this information to race smarter and finish your races more strongly. And the basis of this talk is a study that was recently published in the Scandinavian Journal of Medicine and Science in Sports. And I'm very fortunate to be joined today by one of the authors, Professor Lars Nybo. Welcome.
Well, many thanks for the invitation. And I can say that the first author, Magnus Bach-Claris, he's on his way back from Poland, where he's been doing UCI races. So he's also an enthusiastic bike rider himself, in addition to being hopefully a promising scientist in the area.
That's great to hear. A lot of people will know you and know that you're a professor at the Department of Nutrition, Exercise and Sports at the University of Copenhagen. Before we get into the details of your recent study, I'm very curious to know, what is it that you were hoping to learn when you set out to do this work?
I mean, we've done a lot of studies where we in cycling use it as an exercise model in the lab. But then you can say in the real field, it is a different sport. Bicycling is often an intermittent sport. I mean, power output fluctuates, you do jumps, you do so on. So that is one end of the story. You do a lab study, you do it with a continuous power output, or you use it as a model. And then you have the other end where you just observe power output from professional athletes. And there's been some elegant studies there by Van Erp, where they have analyze different types of sprinters and hill riders. There's also some of the case studies from the Giro d'Italia and so on. So we wanted to bridge somewhere in between this, and that was why we developed this model, so that we could try to study both the fatigue responses, the performance, but also to obtain more physiological data ongoing during this setup.
Would it be fair to summarize it in saying that traditional lab studies don't capture all the changes that necessarily take place during a bike race?
You can try to do a simulation of it, and you can make protocols also in some of these platforms and whatever it is, or in your ergometer or setup. The mimicking of the stuff is not that good.
Yep.
I participated in a lot of podcasts where I said, I think this is one of the flaws in the cycling area, that you, so to say, you think that you can interpretate what's going on in real life settings from your lab studies, and it appears that at least in some cases you can't. You can obtain more information in the field. Of course, that is on the compromise. That is more difficult to control everything. But I mean, we also wanted to test and prove that you actually can do the setup in these settings. Say the settings where we tested is in an old aerodrome, which is closed now, and where we have a circuit of 5 kilometers, which is mainly flat. We take the overall setup. What we did was we started out with some physiological measures, where we measured oxygen consumption. So we moved all our equipment out there. There are some hangars out there where we could place the stuff in. And then we had the cyclists measuring their fat oxidation, their physiological response, their overall energy turnover, and therefore delta efficiency at a given power output. Then we did the first round of formal testing, which consisted of a 100-meter sprint, which we did because we wanted to have some kind of measure of peak power, neuromuscular power, and we both derived the peak and the average of it, but what we report in the paper is the peak power output, so to say, as a clean measure. And we did that first, and then after that brief break, then they did a 5-kilometer time trial, which lasted around 7 minutes on average or something. They did this on their normal bike, so it's not on time trial bike. So then you can say, okay, a 7 minutes effort, that is something which is mainly dominated by your aerobic power, but of course also with your anaerobic capacity on top of that. So you can say what in some is called your V prime on top of your aerobic power. And you can say, why didn't we do it in the reverse order? Because that would be one argument, that okay, in natural racing you would do that, but on the other hand, then the peak power would be much affected by the performance test, whereas in the other way around, it allowed us to get two different power measures. So that was what they did. Then they did 1.5 hours of simulated racing. So like they would do in a race where we had pacing, we had an electrical bike out there which paced them 42 kilometers an hour. Then they did a 20-minute echelon ride where they took turns on shift because we wanted to simulate the fluctuating power output. Then they returned. They had a blood sample where we measured blood glucose and lactate to see what was the level that they had reached. Then they did another round, a peak sprint and a 5-kilometer all-out time trial. Measured lactate again and blood glucose. Then they did another 1.5 hours of simulated racing. Came in again, and after then it was 4 hours testing, peak sprint, 5 kilometers, and then another block, and then the last round of testing after 6 hours. So it was a long day, but they did really well, and I can say that the participants are, you could say, they're all competing in the top national league. Some of them are racing UCI races, some of them have won level 1-1 and 1-2 races. So it's not world-class riders, but it's still riders who compete at this level. So therefore, we also believe that the population and some of the findings, which we will return to, are applicable also for the best riders.
That was actually my next question. Would you deem the results applicable also to lower level, say, age group amateurs, given that these were quite highly competitive riders?
I would say that you could say that we observed that some of them, I mean, with this protocol, some of the best of them, he only lost 2% of his time trial power output, which is comparable. I mean, there's some of the data from the Giro, but again, that is self-paced and they had not done maximal effort, where it shows that the best top 5 finishers, they can produce almost their peak 20-minute effort at the end of a long stage. And here you can say, okay, it's 2% loss. On average, it was 7. So you can say the very, very high fatigue resistant in these semi-professional high level is probably restricted to that particular group. But of course, it can benchmark to say, okay, this is what you can be expect to lower your, I mean, this is an example of, say, extreme durability, very high fatigue resilience in some of, in this population. I think it will be lower the lower the level you go, also as indicated by the studies that has been done, for example, by Fender and others, where it shows that lower level cyclists have lower, or you could say higher fatigue development.
Greater loss of power. With extended work.
You can then say that one of the surprising finding for us was that peak power actually was already lowered after the first block. So the peak power in this group, which was almost 1400 watts, was lowered by 100 watts after the first 2 hours, indicating that just this type of riding, you do the maximal time trial, then you do the echelon riding, changes some kind of muscular properties that don't allow you to have the same power output. But after that, we didn't observe any others. We actually had the reverse hypothesis before, that the loss of neuromuscular power wouldn't occur until you probably were depleted below some critical levels of glycogen. Whereas the time trial performance, the 5 kilometers, that was reduced by 7 watts on average after the 2 first hours, further 7 watts, and then it declined a lot in the last. Again, also some of these anecdotes that has come, that the fatigue really kicks in after they ended up riding 220 kilometers. So after the 200 kilometers, that is really where the fatigue kicks in, which is also supported. But it may also indicate that this type of testing, I mean, the longer, either we should go for longer sprints or some kind of longer power output if it has to be sensitive. Whereas the 100-meter sprint and the peak power is probably not sensitive to grasp this graduate fatigue over time.
Yeah. So there was a difference in the loss of power that you saw for peak power versus the 5-minute time trial test, right?
Yeah. I hope that people will go in and look at the paper, because that is also one of their business. So peak power immediately or declined after 2 hours, and then there was no further loss
Then it
after 4 and 6. Whereas the time trial power declined gradually and even more, and there was also a spread of the individualization, so that the individual points were spread out more. And that was also one of the ambitions, that we wanted to try to see if we could identify some patterns.
Yep.
What was it that characterized the most fatigue resistant where compared to the more fatigue, those with a higher fatigue response?
Off the top of your head, can you recall the spread of power loss for the time trial in the best versus the least fatigue resistant riders?
Yeah, on average after 6 hours it was 7%, but with a spread from 2 to 14. So that was, so to say, the variation that we observed. And we had 3-4 subjects with a very low fatigue.
Say I'm an amateur rider and I want to kind of get an idea of my fatigue resistance or durability. Would the experiment that you did be a decent protocol to start off with to create my own field test?
Well, you could say it's a very long test to do.
Yeah.
And I think that, what is practiced amongst some pro tour cyclists is that they do a prolonged ride, and then they do the effort to try to compare how much power do I lose if I have done a certain amount of accumulated work. I don't believe actually that it's accumulated work. It's probably more accumulated work in red zone, and whether that red zone is then above lactate threshold 1 or 2 or some other indicators. In our work, we tried also in one of our figures is to plot the loss of power against accumulated work and against time above the first lactate threshold. And it appears that there's a slightly lower, it seems to be driven by the time above accumulated time above the lactate threshold. But since the two of them, because we, so to say, when they do the maximal effort and so on, of course, as they accumulate more work, they also accumulate more time above the lactate threshold. But one of the observations when we combine it with others is that riders at this level, they can accumulate and tolerate a lot of accumulated work without fatiguing, as long as it is low intensity exercise.
Yeah.
And that is actually also one of the interesting findings from this, because as I mentioned for you, we measured their oxygen consumption and their fat oxidation. And if we try to calculate and compute some of these numbers, it appears that the fat oxidation that they have, although we provided them with 90 grams of carbohydrate each hour, so they ingested not so much as we see, or at least that there's a report that some pro cyclists ingest, but still high amounts. Then their fat oxidation still increased, and had actually, because some people also say, how important is that? But if we calculate this, then it actually appears that the paced riding, you could say the riding where we simulated that you ride in the peloton, where they did 230 watts or slightly below that energy could actually be covered by the glucose they ingested and the fat oxidation. So if you do that type of exercise, you probably have a very little degradation of muscle glycogen, whereas the glycogen probably declines when you do the intense efforts, which we then in this one simulated by the echelon riding and by the 5-kilometer time trials. And of course, that is where some of the findings from this study also become a little case specific, because if you then had another type, so let's take a ride, one of my favorite races like the Ronde van Vlaanderen classics, where you have all of these small climbs where you do maximal effort, then you probably have another type of fatigue response. So it might be actually that it is somewhat case specific, depending on the landscape, and you could also say we could have done even more jumps. We could have made an even more harsh protocol that would have provoked more fatigue. But this was a balance to say, I mean, at the beginning and when you write it on the paper and before you get it tested off and so on. But it was feasible, and they completed it well.
So fat oxidation increased during the ride.
I mean, we measured it in two different ways. First, the classical, where people come in, face it to the lab, and we do a protocol where they do ramp steps, 100, 130, and then we compute and say, okay, because fat oxidation goes up with intensity until a certain level, and then as you do more intense, the RER declines, and you turn to less fat oxidation. And then from that protocol, we established their fat max and also the intensity eliciting fat max. And then we used that intensity to test them before and after the race with a 10-minute protocol. And in that protocol, they met in with the fed state. So there they were glycogen loaded, and they were instructed to prepare and eat as they would do for a competition. And then it appeared that the fat oxidation in the phase state was higher than when they met in and had, so classic physiology, when you are fed with carbohydrates, you combust more carbohydrates, and therefore your fat oxidation is slightly lower. But then over the 6-hour time course, although they ingested carbohydrate, although they, in each of these intense effort that they had maximal carbohydrate oxidation, very high lactate levels, then it increased. And at the end of these 6 hours, the fat oxidation was equally high as in the fasted state, slightly lower on average, but I mean, with the variation, these types of measurements are difficult to do really good, and is something that we also want to become better at, and it's a challenge. And if you compare, and if you see data from all this kind of stuff, people typically have difficulties in showing how fat oxidation is changing with exercise and so on, because the day-to-day variability. But at least, and we also report the individual values, and we can see, okay, they decline and then they return and get up to equal levels like this. So that was also a little of a surprise for us. And also, you could say in training practice, I mean, some of these people advocating, zone 2 training to stimulate your fat oxidation, and you should avoid doing intervals doing these types of rides, because then your lactate level goes up, and that will screw up your fat oxidation. Forget it. I mean, if you use glycogen, if you use muscle glycogen, then you will have a higher reliance on fat oxidation, and you will drive it up.
I also found it very interesting that you also measured lactate concentrations, I believe, after each time trial.
Yeah.
And these dropped quite considerably, didn't they? I think from 15 millimoles to 7 millimoles after the first and last test from
they
from
gradually became lower and lower.
Yeah.
And of course, this may be indicative of less reliance on your anaerobic capacity. Your W prime is reduced, therefore you have lower lactate levels as your glycogen become depleted. There was also a slight lowering of the peak heart rate achieved. So you can say the lowering of your power output during these 5-kilometer time trials was probably a combination of a slight reduction of your aerobic energy contribution and of your anaerobic capacity. But of course, it also highlights this, that when people get fatigued at the end of rides, say, oh, this is when the lactate kicks in and so on. It's probably other fatigue mechanisms at that time point.
That observation, I wanted to ask you, because that observation that you reported there with the drop in the lactate concentration got me thinking about if it has implications for using lactate measurements to manage or to control your working intensity, say, for instance, during tempo or threshold intervals. If you do really long tempo sessions and you want to use lactate to control your intensity.
Yeah.
If you run that session long enough, would you perhaps get the same effect with a drop in lactate concentration relative to
Yeah, that would be my guess.
intensity, so that could throw off essentially your interpretation?
Yeah. I mean, if you use lactate as a measure of intensity, the best way to get low is to have to do the given intensity in a low glycogen state, because then you will probably have less lactate production, higher reliance on fat oxidation. So of course that could mess up the picture. Again, we observed also, now these peak values that you observed were the peaks that we observed after the 5 kilometer time trial. We also measured them before, and in all of these conditions, after they have done the peloton riding and the echelon riding and the peloton again, then they had pretty low lactate levels. So they, in all instances, returned to levels. Yeah, but I mean, that is also why I'm a little restrictive. I mean, people also have a tendency to consider lactate. I mean, it's a waste product, of course, indicative of a mismatch between anaerobic glycolysis and what disappears into the oxidative metabolism, mitochondria. And if you have a mismatch of that, of course, you will have release into the bloodstream. And then again, that will be a balance about how much is then removed by other organs, where the brain, we know the brain consumes a lot of that lactate when it's high. The liver consumes some other muscles and so on. So all of this is balanced, and that's why I think that I'm not that concerned about it. It can be a good indicator to have that whether you are below the forced lactate threshold or whether you are in the higher area. But using it as, I mean, I would say that it's less sensitive than other types of measures. It can be, it's informative for us as physiologists sometimes, but using it to say, okay, if I have 2.1, then I'm above the 2, then I'm into the yellow zone, I should go lower. And my guess would be that for the same intensity, and perhaps with an even bigger disturbance of muscle homeostasis, if you are glycogen depleted, you could have lower blood lactate levels.
Yeah.
So yes, indeed, that could interfere with such measures.
Thanks for that. That was interesting to get an answer to that question. Looks like from your work and the work of others that intensity is perhaps a bigger driver of the fatigue response than the total accumulated work. Given what we know and what you know from the work that you've done and the science that we have on the field, would you dare give any recommendations on how to train to improve durability or fatigue resistance?
Yes. My best input is that you should focus on training your capacity. So if you increase your lactate threshold, if you increase your peak aerobic power, you will also become more fatigue resistant. The interesting part was that if we look at all of this, we have tried to do a lot of analysis and so on, and it appears that lactate threshold divided by your CDA, so your coefficient of drag and your area, if that is high, then you will also accumulate less time above your lactate threshold, and therefore you will probably be more fatigue resistant. That is stretching the results a little bit here. We also tried actually to analyze all the training that the participant had done in the half year before. So many long rides, much high intensity, and there we found no correlation between total training hours, how much sprint training do you do in a session, how much high intensity. So that was more difficult. We did, however, observe that if the participants with the longest competitive age, so those who have been competing at the national levels for the longest time, were also those who were more fatigue resistant. So that is probably something that the physiology develops over years. You should always be a little, when you look at all of this, you also know all of this where you, from a Wingate test, interpretate fatigue indexes and so on. And then you could always say, if you have a lower peak then you could potentially have a lower fatigue index, but just because your peak is lower. So it's a little restrictive on this. But I still think that the best way to train your durability, as so to say, a term of looking at fatigue resistant physiological resilience, both in terms of losing peak power and this more time trial long power, is to focus on improving your capacity rather than singularly focusing on developing very large volumes, example given, if that doesn't contribute to increasing your...
Thinking out loud here, the argument would probably be if you increase your maximal aerobic capacity, then pushing those same 350 watts will be an easier workload for you internally. So you accumulate less time above your LT2 or FTP or whatever you want to call it.
Also that. And of course, the interesting parts come, I mean, some of these reports that were from the last World Championships where there was evidence, or I mean, I heard himself say that, for example, giving Mads Pedersen, he had 270 efforts where he produced more than 1,000 watts, not just peak, but 3-second averages.
Yeah.
So that may be another story. Again, this with different, and there you could say, okay, what is it that classify this? Why is it that, and that's for me an interesting observation, is that the riders who have a very high intermittent exercise capacity, who can produce these very high wattage, Mathieu van der Poel, Wout van Aert, Mads Pedersen, and then Pogacar, he seems to be able to do it all over the place. But these riders who do it, and the world champion is also the best in an hour effort. But this ability to tolerate that type of challenge of your durability, where you produce, you could say, this is power which is more than double of your aerobic power. That's interesting. If that is also a matter of having a high capacity, so you could say, okay, if you're there whenever you have to produce 1200 watts in order to keep up the pace in one of these smaller climbs, 15-30 seconds efforts, if you there also have a higher power, a peak power, if that also make you more fatigue resistant, because you could say then on the other hand, you could say then you could take a track cyclist which has peak power of 3000 watts, they would probably not be fatigue resistant in this area. So it's probably a combination of that. And likewise here for the bike riders, you could say, okay, who would be expected to have the highest aerobic power? Well, that would be a 4-kilometer time trial pursuit rider, perhaps. So it's probably a matter of having a high capacity, but also that it in the training and in the races where it's challenged consecutively times throughout races, that probably also has some important stimuli to this aspect.
Well, Lars, thank you so much for joining us today and taking the time out of your day to share your insight. For anyone listening, I know that you're also quite active on Twitter, so I would recommend everyone who's interested in updates on cycling science to follow Lars on Twitter. I'll make sure I drop the link to your Twitter in the description below.
Yeah, thanks.